Welcome to the Explainer. Today, we're going to break down meta-analysis, a really powerful tool scientists use to find the signal hidden in the noise. It's how they can take a bunch of conflicting studies and find a single, more reliable truth.
So let's dive in. We've all seen those headlines, right? One day, coffee is a miracle cure. The next, it's terrible for you. Why does this happen? Well, it's because any single study is just one piece of a much larger puzzle. It's like a single snapshot, not the full movie. And as you can imagine, different snapshots can look very, very different. So, to solve this puzzle, researchers turned to meta-analysis. Now, this isn't a brand new experiment. It's actually a study of the existing studies. The whole point is to gather up all those individual snapshots and stitch them together so we can finally see the big picture, that full movie we were talking about.
And when you do a meta-analysis, you're really trying to do two things. First, you combine all the evidence to get a best guess of the overall effect. But second, and this is where it gets really interesting, is you try to explain why the results are different from one study to the next. These differences, what researchers call interaction effects, show you where a theory holds up and, just as importantly, where it breaks down.
Now, doing one of these involves a whole series of critical choices. So today, we're going to walk through that journey, and we're calling it the researcher's crossroads.
Okay, our first stop is the most fundamental choice of all. And honestly, it's almost philosophical. It's about deciding on the very nature of the truth that you're even looking for. And that boils down to this crucial question. Are all of these different studies trying to measure one single, unchanging truth, or could the true effect actually change depending on the context? Your answer to that question determines the entire statistical model you're going to use. So you have two models here, the fixed effects model and the random effects model. The fixed effect model assumes there's only one true answer out there, and all the variation you see is just random noise. But the random effects model assumes the true effect itself can actually be different from study to study. And you know, in the social sciences, where context is everything, the random effects model is pretty much always the right choice. All right, so with our worldview chosen, the next crossroads is all about selecting a common language, a single way to measure things so that all these different studies can actually talk to each other. And this common language is called an effect size. It's a single, standardized number that captures the core finding of each study. Think of it like a universal measuring stick. It puts every single result on the same scale so you can finally make direct, apples-to-apples comparisons.
Now, researchers usually choose between two main languages. First, there's R, the correlation coefficient. This is for observational studies asking how related are two things. Then there's D, the standardized difference, which is perfect for experiments asking how different is group A from group B.
And this choice, it really highlights a divide in the scientific world. You can see here that journals that focus on things like management research overwhelmingly use R. But journals that summarize experiments, they heavily favor D. So the language you use really depends on the world you're studying.
So the choice of language often leads researchers down one of two paths, to one of two competing toolkits for doing the actual analysis.
Okay, so the two main toolkits in town come from groups led by Hedges and Schmidt. You can think of it like this. The Hedges approach is all about precision. It gives more weight to bigger, more accurate studies. The Schmidt approach, on the other hand, is really focused on correcting for statistical imperfections, all the little artifacts that might be muddying the waters and hiding the true relationship.
So, the Schmidt method, it's kind of like being a detective. First, it figures out all the variation across the studies. Then, it carefully identifies and subtracts all the variation caused by statistical noise, things like using an unreliable ruler to measure something, and only what's left over, the true variance, gets analyzed. It's all about getting closer to the real story.
So with all these different crossroads and choices, how do we make sure the final result is actually trustworthy? Well, thankfully, the field has developed a pretty clear guidebook of best practices.
You know, a ton of the most important work actually happens before a single number gets crunched. A good researcher has to define exactly what they're looking for, create crystal clear rules for what studies get in and what gets left out, and then search absolutely everywhere for relevant studies. And the guiding principle through all of this? Transparency, transparency, transparency.
So, once you got all your studies, the big decisions just keep on coming. Are you going to correct for that statistical noise we talked about? And, maybe most importantly, you have to actively hunt for potential biases in the literature. And the biggest one of all is something called publication bias.
Publication bias is kind of the monster under the bed of science.
It's this natural tendency for studies with exciting, positive, statistically significant results to get published. Meanwhile, studies that find, well, nothing, they often end up in a file drawer, never to be seen again. It's not usually malicious, it's just that we as humans tend to favor exciting discoveries over a finding of, nothing happened here.
So what's the big deal? Well, the consequence of this bias is that the scientific record itself gets skewed. When you plot out the studies, these missing null results create a lopsided, asymmetrical shape. And this can make an effect look way stronger or more consistent than it actually is, because you're not seeing the whole picture.
And this brings us to our destination, the entire point of this whole rigorous, complicated journey in the first place. Building a scientific record that we can all trust, one that's transparent and crucially replicable.
See, before meta-analysis, scientists would write these things called narrative reviews. And as this quote says, they were subjective. Two experts looking at the exact same evidence could come to completely opposite conclusions. Meta-analysis was created to fix that, to be objective, to be data-driven, and to be replicable.
And here's the ultimate challenge, the final twist. After walking through all of these crossroads, you can see that if a researcher isn't totally transparent about every single choice they made, this incredibly powerful tool can become just as subjective as the old method it was designed to replace. And that, as the authors say, would be a terrible irony.
So when you boil it all down, a great meta-analysis isn't just a summary of findings. It's a transparent, honest argument. It's a roadmap that details every choice made along the way, allowing anyone to follow the path, check the work, and build on it in the future. Which leaves us with a final, big question to think about. If this is the gold standard for creating reliable knowledge, how much of what we think we know has actually been put to such a rigorous and transparent test?